Okay, so here with number 12, we have a free energy diagram. And so if we look at the y-axis, we have energy, or the free energy of the reaction. And then on the x-axis, we have the extent of the reaction. So here where it's 0 on the x-axis, that's where we're completely at reactance. Whereas at 1, we have 100% products. Okay. And so this is the plot where you can think of something like a tennis ball rolling down. Oops, that's my tennis ball. It rolls and lands at the bottom of the well. Okay. And that place where it ends up landing is the point where we consider to be equilibrium. So at the energy max or minima. So this is going to be for equilibrium position. Okay, so let's look at the statements that they have us evaluating. The first one says point A represents equilibrium. Okay, and we decided that's false. And also point A there would be our initial starting place that corresponds only to reactants. Okay. For 2, it says KEQ is less than 1. Okay, so let's look at where that equilibrium spot is. And so because the equilibrium value falls more on the reactant side, that means it's a reactants favored process. And when something favors reactants, we know that KEQ is indeed less than 1 because it's an expression of products divided by reactants. Okay. So next up at point D is Q less than KEQ. Okay. So at point D, we're more toward products on the plot. So we're going to have extra products. And because our expression is products over reactants, if we have extra products, Q here would be greater than KEQ. Okay, so this is false. Okay. Arrow B represents the magnitude of delta G of reaction. And so we want to remember that the delta G of the reaction is equal to delta G for the products minus the delta G of the reactants. And we can see that that's in fact the difference represented by arrow B. So that statement is true. And then lastly, we have at point C, delta G of the reaction is equal to 0. And so we know delta G is equal to 0 when we're at equilibrium. And we already decided that equilibrium is at point C, so this checks out. That would make sense. Okay, so the correct answer for this is option choice E. Okay, so now in problem 13, they give us this nitrogen-containing compound and want us to describe it in terms of an acid or a base. Okay, so first let's just ask ourselves, is this one of our 7 strong acids or 8 strong bases that we've memorized? Hopefully it's evident that this is not one of our strong acids or bases. So we can eliminate the strong options. Okay. So, what I'm going to look at next is what's going on with the nitrogen. So that nitrogen, if we were to draw the full Lewis structure, we'd have carbon with 3 hydrogens around it. A nitrogen. And then 3 hydrogens attached and a positive charge. Okay, so this nitrogen has 4 groups surrounding it. When a nitrogen has 4 groups, it has nowhere else to put any more hydrogens, so instead it will end up giving up a hydrogen. So this will in fact be a weak acid. And we can go ahead and write the full equation. So after this reaction would be in equilibrium with the neutral amine and then hydronium ion. Okay. And so then this neutral ammonia compound would be the conjugate base of our original species. Okay, so the answer is just A. Okay. And number 14, we're making some concrete. We're mixing some calcium hydroxide, calcium carbonate in a container, and have some CO2, some water. And they're asking us what must be true if the Kp for this reaction is 2.2. So, with equilibrium, it's always a good idea to start by writing your equilibrium expressions. So I've done that here. And you might be saying, hey, Virginia, there's 4 things in our reaction, but you only put 2 in the K expression. What's up with that? But then you would realize the reason I didn't include the calcium hydroxide or the calcium carbonate is because they're solids. So, they don't belong. Okay. So, the first statement here says Q is equal to 2 times 10 to the minus 4th. So let's go ahead and plug in our pressures for water and for CO2 and see if that would give us that Q. Okay, so if we evaluate this Q expression, plug it into our Chem 112 approved calculator, we get this value, 0.002, which is indeed equal to 2 times 10 to the minus 4th. Okay, so this first statement checks out. That's true. Okay, so then they ask, will the reaction proceed to the left or to the right? So let's compare our Q to the KEQ. So we can see from these numbers that the Kp of 2.2 is indeed quite a bit larger than the Q of 2 times 10 to the minus 4th. So, if we have a small Q, that tells me we must have too many reactants. Because it's products over reactants. So if we have too many reactants, we've got to make more products, and that's going to be a shift to the right. for the final statement, that's going to be false, of course, because for the reaction to be at equilibrium, we would expect Q to be equal to KEQ, and there would be no shift. Okay, so the correct answer is B, which is just that the first and third statements are true. So now they want us to say what the conjugate acid of HPO4 2- is. So in order to have a conjugate acid, the molecule must be acting as a weak base. Okay, so we can go ahead and start by writing the base hydrolysis reaction. Okay, so now that we have our base hydrolysis reaction, we can see that our original species has acted like a base and has picked up a proton from the water to become H2PO4-. Okay, so these two are a conjugate pair. Okay, and so this H2PO4 is the conjugate acid. So any weak base has a conjugate acid. Any weak acid has a conjugate base. And so when you're trying to distinguish between options like C and D, just don't forget that when you take a proton, it's H+, and so the charge will go from 2- to just 1-. And you can look on the right side of the reaction, we have an overall -2 charge, and on the other side of the reaction we also have an overall -2 charge. So you can check for charge balancing too. Okay, here we have a question where they're asking us for which of the following reactions is delta G not of reaction equal to delta G standard of formation. So I've written here how we think of this, which is the products minus reactants rule. And what they're alluding to is, when is this portion going to be equal to this portion? And so for that to ever be the case, this third term, or the delta G of formations of the reactants, must be equal to 0. Okay, but how do we know when it's equal to 0? And so we have to know whether an element is in its standard state. Okay, so I wrote a little table about how to tell when elements are in their elemental state, because at their elemental standard states, the delta G of formation and the delta H of formation is equal to 0. Okay, so looking at the periodic table, we can assume that most everything is solid at standard state. Like gold is a solid, silver is a solid, carbon's a solid, iron is a solid. You know, some of those things make sense. And then we have some exceptions. We have mercury, which is a liquid. A confusing exception is that the noble gases are indeed gases. And then we have the diatomics. And so I have a way to help you guys try to remember the diatomics. Okay, so I have this saying for the diatomics that's, have no fear of ice-cold beverages. And from this you can get H2, N2, F2, O2, I2, Cl2, Br2. Okay, and this can also help us remember the phases. Because if you think about ice, Ice is a solid. Do you know what that means? I2 is a solid. And beverages, those are liquids. So Br2 is a liquid. And then the rest of these are gases. Okay, so now that we have that all laid out, let's look at the reactions. Okay, so in A, H2 gas, that's in its standard state. F2 gas, standard state. So it seems promising. The only issue is here we're making 2 moles of products. So we would sort of have where delta G of the reaction ends up being 2 times the delta G of the formation. And so that's doesn't match with what they're asking us, which is why that gets ruled out. We just want to make 1 mole of product. Okay, and B, our reactants are complex molecules. It's not just one element on its own. And so both of these would have some delta G formation. And so B is out. Okay, for C, lead, that's not one of our exceptions, so that's good to be a solid. But I2 is supposed to be a solid in its standard state, so this would not be standard. So C is out. Okay, magnesium solid, that would be a standard state. Oxygen gas, standard. And we're making just 1 mole of product. Okay, so that seems promising. Let's check the last one though. HCl, not just one element on its own, so that's no good. And also, we know that bromine is a liquid in its standard form, so E is out. So that makes D the correct answer here. Okay, in number 17 we have a Le Chatelier problem, where we have this reaction going on in a container, and we want to decrease the partial pressure of ammonia. So let's remember that. So I've gone ahead, we have an equilibrium problem, so I wrote an equilibrium expression. And we can use that to help us a little bit too. So the first thing they're asking us about is if we increase the O2 partial pressure. Okay, so if we increase a reactant, that causes the reaction to shift to the right toward products. And so when that shift happens, the oxygen that we've added is going to drag some of the ammonia with it, and that pressure will decrease. Okay, so this first statement seems like a good idea. The second statement says increasing the temperature of the vessel. Okay, so they tell us that our delta H is negative 64.5 kilojoules per mole. So this is exothermic. Heat is exiting. And so it's going to kind of be like a product. It's going to come out of the reaction. Okay, so now that we've considered it as a product, if we were to increase the temperature, we would be adding to the product side, and the reaction would shift to the left. Okay, so that would end up increasing the pressure of the ammonia. So this would be no good. Okay, the third statement says decreasing the volume of the reaction vessel. Okay, So, you know how dorms are small? I'd much rather live in a single than live in like a triple or something, right? The more people you squeeze into a tight space, the more uncomfortable it is. And gases feel the same way. So we know that decreasing the volume would cause them to prefer to be more on their own, and we want fewer moles of gas. So if we look at the reaction, on the reactant side we have 7 moles of gas, and on the product side we have 8 moles of gas. So compressing this reaction would cause it to shift to the left toward the fewer number of roommates. And then by shifting to the left, we would increase the partial pressure of the ammonia. So the third option is out. Okay. Now, say if we increase the water partial pressure, so we'd be adding in a product. If we add in a product, we're going to shift toward reactants, which would cause an increase in the partial pressure of ammonia. So this would also not end in the decrease of the partial pressure of the ammonia. So the only correct answer here is the first statement, corresponding to option A.